Okay, this is question 11. So notice that friction is being ignored. So in this case, meaning that whatever work done along this slope must be equals to the gain in the PE by the car. So once you know that, even though they didn't tell you how much force is given by the engine, you can just equate the work done to the gain in PE and you can find it out. So normally, if this kind of question is given in paper 2, they will follow up with a question and ask you to calculate. So once you know the work done, can you find me the force given by the engine? Okay, and then once you know the work done here, you just divide by the distance. You can find out the pushing force from the engine. Okay, question 12. Please take note, all these particles are not your air molecule, they are dust particles. Air molecules are too small to be seen. Okay, so what happened is that in this question, let's analyze every statement and then we analyze what is wrong about the statement. So A, the air molecule are in continuous random motion. This is correct because as you observe the smoke particle is going everywhere in a randomly manner. So then you can deduce that, okay, the air molecule must be colliding with them in a random manner as well. So that's why A is correct. Okay, B, they, remember this they refers to the air molecule. So what happened? So what this statement means is that the air molecule can be seen through a microscope, and that is wrong. Microscope cannot see molecules. Okay, then the C statement, air molecule move because of collision with smoke particle. That is not true. The smoke particle is the one that is getting colliding with the air molecule, and the smoke particle moves because of the collision. Okay, so this is wrong because the cause and the effect is reverse. Okay, the air molecule moves because they are in constant motion. Okay, they are having energy. Okay, and they actually are hitting on the smoke particle, and that gives the smoke particle movement. Okay, air molecule move more quickly when they are hit. This statement is correct, but that is not what this experiment has demonstrated. So D, it is a true statement, but unfortunately it is not what this experiment has demonstrated. Okay. Okay, question 13. Question 13, what they actually did is that they are trying to use the steel ball to simulate the air molecule, and they are trying to use this experiment set up as a model to explain why when the volume decreases, the pressure increases. Okay, so which of the following describe what is being modeled? So let us go through it one by one. So when the gas is compressed, then heat. So what happened is that the weight on the wooden disc, this one, is trying to simulate where the gas is being pressed down. So that's why gas is being compressed. And then the piston has to vibrate more rapidly to return the disc to the original position. So what this piston is simulating is that this piston acts as an energy source to the steel ball. So when this piston moves up and down more violently, what this piston is doing is that it is providing energy to these steel balls. Okay, so this piston modeled as an energy source, and therefore is actually modeling when the gas molecules are being heated. So that's why statement A is correct. Now let's look at B. Gas is cool. So when gas is cool, a correct model will be the energy source should reduce its frequency of vibration or decrease its amplitude of vibration. So clearly the weight itself is not simulating the gas is cool. So that's why B is wrong. Similarly for C and D, whenever you are seeing that the gas is being heated, what this statement is that is saying that energy is being added to the system. And by adding a weight on top, this is not simulated. by adding a weight on top, you are either reducing its volume or you are compressing the gas. So actually it's quite straightforward. B, C and D is a no-no. Okay. Again, it seems that a lot of schools like to give this kind of question. What you need to take note is that if you can remember formula, you can use the formula directly. But if you are like me who don't like to remember formula, just remember you just need to sketch a very simple graph of temperature versus the expansion in length. Okay, so what I did is that they tell you that the length, let's say, is all started at here, right? You see this arrow start here, this arrow start here. So let's take this as reference as 0. So at 0, this is where minus 10 degrees C will be, right? So I have this point here. You need not have 0, 0. You can have 0 minus 10 is alright because it's just a sketch. Then after that, you know that at 110 it is 25 cm. So 25 cm correspond to 110. And then you are actually assuming the expansion to be linear. So just draw a straight line here. Then the question asks you, what would the temperature be if now the length is 15? So this sketch actually reduced this question to a very simple mathematical question. So what you do is that you try to find the gradient between these 2 points. Then you find the gradient between, and you know that you can equate the gradient of these 2 points to the gradient between these 2 points because it's a straight line, right? So that's what I did here. So this is the gradient between point A and point B. And then I equate it to the gradient between this point, and they have to be the same because they are on the same line. So once you solve this equation, you will be able to find the temperature. Okay, question 15 is, I find it interesting. Now, once they are talking about thermocouple, you can no longer use this kind of, actually you can still use this kind of sketch. But in thermocouple, you know that the difference in temperature is directly proportional to the current being induced. So difference in temperature is just your hot temperature minus your temperature at the cold terminal, and it has to equate to Ki, because this relationship will give you this equation. You learned that in your mathematics. So what I did here is that I just put in the information given to me in the question, that the hot junction is in steam, boiling water, which is 100 degrees C, and the cold junction is in melting ice, so at 0. So once I have this, I put it in the formula, I can find out what is my constant. Then I apply it to my new context, whereby the cold junction is still at melting ice, but now my hot junction is an unknown temperature. Now, even though the reading is on the other side, the reading on the other side simply tells you that now your current is in the negative region. So just add a negative sign, substitute it into your formula, put in the value of K, which is your constant. The formula will take care of itself and tell you what is the temperature at the hot terminal. So just believe in the mathematics and the relationship, you will be able to find out what is the answer. Okay, question 16. Now question 16 is quite typical. It appears in the 10-year series quite often. So what happens is that the heat will travel from high temperature to low temperature, and since there is only air here, and if you look at convection, why convection is not considered here is that because the air around the heater is going to get heated up, and heated up air will get lower density, so it will only rise. So therefore your hot air will not come to your metal plate which is on the side. So that's why convection is not the main mode of heat transfer between the heater and the plate here. Okay, and conduction is definitely a no-no because there's no contact. Air is a bad heat conductor. So it leaves us with one heat transfer method, which is your radiation. So what happens is that the heat will radiate to the metal plate. The metal plate will absorb the heat radiation, and then because there's contact between the wax and the metal plate, so through conduction, the metal plate will then melt the wax. So therefore your answer will be first radiation followed by conduction, your option C. Okay, this when ice is changed into water is actually your freezing. Okay, so let us look at these three statements. Work is done in breaking the molecular structure of ice change to water is your melting, not freezing. So this is your melting. So work is done in breaking the molecular structure of ice in solid state, that is true. Okay, because you want to change it into liquid state. Internal energy is increased, that is true, because now your molecules are moving further apart. So the internal potential energy is being increased. Now, some of you may ask me, why is it that when the molecular bonds are being broken, the energy increase? Shouldn't the energy be used to weaken the bond or to break the bond? Now, when you go to uni, there will be a more detailed explanation in this. But for now, you can think of the molecular structure as this model. So what happens is that you can imagine that molecules are like balls, okay, and they are being linked to each other by a spring, a tiny spring. So this tiny spring is like your intermolecular bond. So when this thing is going through melting, of course the bonds are going to be stretched further apart. Now what happens when you start stretching a spring? You are actually storing energy in the spring, right, when you stretch it, right? So similarly, when you stretch the bond or when you weaken the bond, what you are doing is that you are increasing the potential energy in this spring. So that's why your internal potential energy will increase whenever your intermolecular distance is increased. Okay, so yes, during melting, the internal energy will definitely increase. Number 3, energy is absorbed to raise the temperature, and you know that during melting, temperature is constant, and therefore, statement 3 is a no. Okay, question 18 is a very typical heat capacity question. Okay, so let me see what I have done here. Okay, first, they give you the context of how much energy is used and how much temperature has rise. So from the first context, you can actually work out what is your heat capacity here. So work out your specific heat capacity and then apply it to the second context, and you will find that, okay, to cause the temperature to rise by 80 degrees, you would need this much of energy. So if you are having a heater with this power rating and you want to produce this much of energy, just use your P equals to E over T, and you can find out how long does it take. So this is in seconds, remember, because the SI unit here is seconds. So just divide it by 60 and you can convert it into minutes. Okay, whenever you are doing questions like question 19, when you are asked to deduce the image or whether you can see the image or not through reflection, first thing you need to do is use your ruler, extend this mirror surface as the boundary is okay, then measure the object distance here. So down here is about 1.5 cm. So do the same thing, locate the image, okay, at 1.5 cm. Then all you need to do is that now from the image, draw a straight line to the point of observation. Okay, so what happens is that this straight line, because light travels in straight lines, so this straight line actually provides you with a guide on whether or not the light will be reflected into the eyes of the observer. So what happens is that if you look at here, if you put a straight line, this is straight line, you will notice that Q cannot see anything because there's no mirror here to bounce off the light to it. The light will just carry on going straight. And if you look at R, it's the same thing, there's no mirror surface here, so there will be no rebound, so R can see nothing. If you see S, you realize that, oh, okay, there's a rebound surface, definitely you can get it back to O. So S can see something. Similarly to T, I know it is very short, but like I said, this method is a foolproof method. So just draw it here. You will notice that, oh, okay, you can still reach O. Okay, now, some of you may ask me the question, teacher, how come you know that this point will always link to the object O? Well, because the object O is the source of the light, right? That's how you see things. Okay, so the light must have traveled from O to the mirror, so that's why I'm drawing this ray. Okay, it's just that I am trying to reverse the process and deduce whether S can see the object or not. So whenever you see this kind of question asking you whether you can see the image or not, the first thing you should do is locate the image. Then after that, draw these guidelines and see if the observer can see the image. Okay, because the observer is looking at the virtual image here. So therefore, there must be a straight line between the observer and the virtual image. Okay? Question 20, you look at the graph and you look at how the context of the experiment. So the context of the experiment is from optically less dense to optically dense, meaning that you can use n equals to sine I over sine R. Okay, this equation is only applicable for light entering from less dense to optically denser medium. So once you see this, you notice that, oh, okay, my y-axis is actually my sine I, my x-axis is my sine R. So meaning that the gradient here, the gradient in this graph will be the optical density, the refractive index. Okay, the refractive index. So once you know the refractive index, you can then find out your critical angle using this formula. So you get the answer.